Good morning, everyone. Today, I'm excited to share a concept that bridges two critical fields, control system and power engineering. The topic is fast frequency response in data centers. We often think of data centers just as massive facility housing servers that consume huge amounts of power. But what if we change our perspective? What if we look at a data center not just as a load, but as a highly responsive controller capable of stabilizing our entire power grid? Today, we will apply the fundamentals of control system, specifically closed loop, theory, and Laplace transform to demonstrate how data centers can prevent grid frequency collapse. Let's begin by defining the plans we are trying to control. In control theory, the plant is the physical system we want to manage. Our plant today is the modern power grid. As you know, we are transitioning globally toward renewable energy. Why this is great for the environment? It creates a severe engineering problem. Traditional power plants use massive, heavy, rotating turbines. This turbine provides physical inertia which acts like a giant flywheel, stabilizing the grid frequency. When we replace this with solar panels and wind turbines, we remove that heavy rotating mass. We lose system inertia, denoted as H. The result, the plant becomes highly vulnerable to sudden disturbance, like a generator tripping off, act as a step disturbance. Without inertia, the grid frequency drops dangerously fast. This is a high rate of change of frequency, or ROCO F. If it drops too low, hitting a deep frequency nadir, the entire grid can collapse. We desperately need a fast-acting controller to fix that. Unlocking the data center as a high-speed actuator. So, where do we find this fast actuator in modern data centers? A large commercial data center can consume tens of megawatts, but this power is not just a static block, it's highly controllable. We can break it down into three main components. First, the IT server P_SRV. Modern servers use dynamic voltage and frequency scaling (DVFH). This means we can instantly throttle down CPU workloads to reduce power consumption in a matter of milliseconds. Second, the cooling system P_Cool. Cooling systems have high thermal inertia. They react slowly over minutes, meaning they provide a stable baseline power during the subsequent events we care about. Third, the UPS and battery P_UPS. Data centers have massive battery backups with bidirectional inverters. This can inject active power back into the grid in under 100 milliseconds. The net power exchange with the grid is P_DC equal P_SRV plus P_Cool minus P_UPS. This gives us a highly agile megawatt scale actuator. Upgrading the controller, physical versus electronic. Let's compare the old controller method with our proposed electronic method. Traditionally, grid frequency was controlled by the mechanical kinetics energy of synchronous generators. When frequency drops, mechanical turbine governors slowly open valve to generate more power. This actuation delay takes about 2 to 5 seconds. In a low initial grid, 5 seconds is too late. The system might already be unstable. Each contrast our data center uses virtual inertia. The source of the response is software workload modulation and UPS battery. Because everything is managed by digital signal processing, the actuation delay is less than 0.15 seconds. We are essentially replacing a slow mechanical governor with a sub-second digital P-controller, proportional controller tuned by Laplace transforms. Breeding grid to hardware closed loop architecture. To complement this, we design a classic closed-loop architecture. The feedback signal is the grid frequency deviation delta F. The data center is FFR controller. Continually monitor these error signal. Our controller logic is bidirectional. If there is an under-frequency event, delta F is negative. The controller acts to shade the IT load and discharge the UPS. If it's an over-frequency event, it absorbs load and recharges the UPS. The output of the controller, which is the aggregated strength in data center power, delta P underscore DC, is then fed back into the power grid to counteract the initial disturbance. This closes the loop. Defining the system time domain differential equation. Before we can tune this controller, we must define the system mathematically. In the time domain, the grid mechanics are governed by the swing equation. The rate of change of frequency depends on the imbalance between mechanical and electrical power, system inertia H, and load damping D. On the controller side, the data center is response isn't perfectly instant. We model it as a first-order lag system. The key parameters here are tau underscore DC, which represent the physical delay of the inverters and software, and K underscore DC, which is the proportional gain of our controller. But analyzing coupled differential equation in the time domain is messy and difficult for controller tuning. Transformation to the S-domain. This is where the magic of control systems comes in the Laplace transform. We take that messy calculus in the time domain and apply the Laplace transform to convert it into the S-domain. This transforms our differential equation into manageable algebraic equations. The mathematical leap is crucial. By working in the S-domain, we can directly analyze closed loop stability, map out the poles on an S-plane, and calculate the optimal tuning parameters for our P-controller. We shift from observing physics to engineering a stable system. The closed-loop transfer functions reveal. Applying this to our system giving us the closed-loop transfer function. Look at the denominator. 2 plus d plus k underscore dc 1 slash 1 plus tau underscore dc multiply s. This equation tells the whole story. The 2 term represents the physical inertia that is disappearing from the grid. But look what we added, k underscore dc. This is the electronic governor. The math proof that our software control gain k_dc acts in direct opposition to the disturbance, actively replacing the missing physical machinery. S-domain, insight, system dumping, and root lookup. What insights do we gain from this S-domain analysis? First, enhance system dumping because k_dc sits in the denominator alongside d, increasing our proportional gains directly increases the effective damping coefficient. It forces oscillations to decrease rapidly. Second, virtual inertia. Because our system delay tau_dc is engineered to be extremely small, less than 0.15 s, the electronics loop mathematically behave just like a heavy physical rotor. Finally, root locus stability, but properly tuning k_dc, we ensure the system pole remain deep in the left half of the S-plane, guaranteeing that our aggressive P controller doesn't intro high-frequency instability. Empirical validation, the step response. Let's look at the result. We simulate a severe step disturbance at 200 MW generator tipping offline as T equals 5S. The dashed black line is the integrated plan. The black line, the frequency dropped sharply to 59.66 Hz. The blue line shows what happens if we only use the UPS. It helps, but we can do better. The solid gold line is our coordinated FFR, our optimized closed loop system. Notice two massive improvements. 1. Overshoot nadir. The severity of the frequency drop is reduced by 57% because of our high system damping. 2. Settling time. The system recovers to steady state 34% faster. Component to control realization. How did the data center actually achieve this? This graph shows the hybrid actuation. Immediately after the disturbance, the UPS battery provides a blue force transient response. Let the shape blue spike. Simultaneously, the IT service begin throttling their power, the less curve. This provided sustained support to collect the other while the physical grid takes time to recover. The best part, Because of the precise tuning derived from our S-domain analysis, this entire operation limit computational takes delays to less than 2%. The data center stabilizes the grid without violating its service level agreements. Reference and conclusion. In conclusion, by applying fundamental control system theory utilizing Laplace transform to design and tune a closed-loop controller, we can transform a data center from a passive consumer into a virtual synchronous machine, ensuring the stability of our future renewable grid. Thank you for your attention.